Hello everyone and welcome to our finale for the Compass seminars for this year, it being the 51st Compass seminar. Today we'll be hearing from Dr. Milan Curcic, who is an assistant professor of ocean sciences here at Rosenstiel, as well as core faculty at the Frost Institute of Data Science and Computing. After receiving his Bachelor's of Science in Meteorology from the University of Belgrade, as well as his PhD in Meteorology and Physical Oceanography from the University of Miami, he now focuses his research on ocean waves and their role in the Earth system, but when not looking at waves all the time on computers, he focuses on hiking and reading with his family. And without further ado, we'll be hearing from Dr. Milan Curcic.
Thank you, Sam. Thanks for having me. The name of my talk is Dispersion of Short Waves Riding on Longer Waves. And if dispersion is unfamiliar, it really just means this is about how do the properties of short waves change when we have some ambient longer waves propagating through their field. This was a pet project of mine for a few winter seasons. I would work on it for 2 weeks during the winter break and then leave it. So this year I realized it may be mature enough to get some feedback from the community. I presented this last week at WISE. WISE is an annual conference that focuses on ocean waves. So many ocean wave experts show up there. I got overall good and supportive feedback on this. Okay, so I'll be walking a lot back and forth because I don't have a screen in front of me. So I'm presenting from the big screen. I'm also using it as my own reference. So short ocean waves are modulated by ambient longer waves. And modulated just means that their properties, such as their wavelength, frequency, how fast they move, they're changed by ambient currents. And in this specific case, ambient currents are induced by longer waves. This problem has been well studied, but still not yet fully understood. And over decades there has been theory work, observational. There are many processes that contribute to this. You can hear about hydrodynamic modulation, which has to do with modulation due to stuff going on in the water. You can hear of aerodynamic modulation, meaning when you have wind blowing the ocean surface, the geometry of the ocean surface that's induced by the waves, that changes the airflow and thus the response of the short waves. Here we're going to focus completely on hydrodynamic modulation, and this process is important for at least remote sensing. So when you have I'll go into more detail on each point. So I said remote sensing, numerical wave prediction, and in situ measurements. So before illustrating each of these important aspects, let's just get an overview of the basic physics. So we have a linear sine-like wave. So this is a long wave propagating from left to right on this plot. And this wave induces orbital velocities underneath the surface. So at the crest of the wave, you will have a forward velocity of ocean particles. And this velocity decays with depth. And likewise, because of the decay with depth, at the troughs, you have a backward velocity that is somewhat lower in magnitude. So forward velocity here and backward velocity here and their difference in magnitudes induce convergence on the front face of the wave and divergence on the rear face of the wave. Now, if you now suppose that you have stuff on the surface, either being a tracer or something like short waves that are propagating, this convergence and divergence causes basically an increase in quantity on the front face and a decrease on the rear face. And what that means for short waves is that short waves will bunch up on the front, and they will dilate on the rear. This bunching and dilation of short waves, changing their properties, so their wavelength changes, thus their frequency changes too, phase speed, group speed, all that. The long waves induce not just, I said induce orbital velocity, but orbital means that, water particles are moving in approximately in circles underneath the surface. So it means that you not only have horizontal velocities, but you have vertical velocities. So vertical velocities are largest at the front face, upward and downward. But actually the change in time of these vertical velocities also induces vertical accelerations, downward at the crest and upward at the trough. Now what these accelerations do is effectively change the apparent gravity of the short waves. And when we get to the dispersion relationship, you'll see that the properties of the wave depend on the magnitude of the gravitational acceleration, because gravity is a restoring force for gravity waves. So combine this, in summary, this convergence and divergence on the front and rear faces of the long wave, and the changes in gravity along the phase basically gives you a phase-dependent properties of the short waves that are just propagating from left to right. Now, the short waves propagate with their group speed, and that group speed is in general significantly higher than this orbital velocity. So, but it is smaller than the phase speed of the long wave. So if we follow the long wave in this frame, short waves are actually moving right to left in that moving frame of reference.
So,
Go ahead.
When you say short waves will bunch up on the front face, does that mean they are bunched up on the crest?
Yes. So now mentioning the moving frame of reference, I said that the short waves are moving from right to left.
Yeah.
So all the bunching action will occur as they travel on this side, and they'll be maximally bunched at the crest,
Right.
and minimally bunched at the. So it's useful to think of this as a forcing rather than a finite state.
Yeah.
But we'll get to this through the equation.
Yeah.
And yeah, please interrupt with questions or hey, explain this a little more at any point. I have more time than I have slides, which allows me to just go in more depth.
Can I ask one question? Is the convergence is the same magnitude as the divergence? For the same, is the magnitude of the convergence is the same as the divergence?
Yes, it is. Except there will be some differences in the sense because the group speed of the short waves will change. Actually, waves spend more time on the crest than they do in the trough. So that will create some asymmetries there. But, just written out like this, yeah, they're the same magnitude. Okay, so I mentioned, that these things are important for remote sensing, wave forecasting, and interpretation in situ measurements. This is just my drawing of a satellite that carries some radar, and it has a beam pointed down at the wavy ocean surface, and the return of the radar signal basically resonates with the Bragg waves, the short waves on the surface. And based on that return, we can infer properties of longer waves, even though we're not directly measuring these longer waves. We can infer their properties based on the short waves. So you can see that us understanding well and knowing how much these short waves are bunching up in ambient long waves is important for interpretation of these signals. Regarding the importance for numerical wave predictions, so wave forecast models provide critical information for marine operations and coastal communities, but they also provide surface boundary conditions for atmosphere and ocean circulation models. So that's pretty important. And how wave forecast models calculate that is they solve the wave action balance equation. We'll get to that. And this equation includes empirical source and sink functions. Now, sink, you can imagine, because it's a sink, what could be a typical sink for ocean waves? It could be wave dissipation, so wave breaking. And state-of-the-art wave dissipation functions, for example, Leonel Romero's, that is now in WaveWatch, parameterize this modulation effect as a cumulative mean square slope. And what that means is, basically, in the wave model, you have a bunch of different frequencies of waves that are being computed. And basically, this term counts how steep are, cumulatively the long waves for any single wave for which we want to know how much it's going to break. As you can imagine, if I'm a short wave and there's a lot of long waves that are very steep, I'm more likely to break than if the long waves are gentle. And that's what this parameterizes. And what we're seeking in this talk actually factors into this. And this has typically been, estimated based on a mix of theory, lab, field measurements. Okay, I mentioned the importance for the interpretation of in situ wave measurements. Suppose that you have a fixed wave sensor and that you're measuring only the short waves that are, let's say their wave number is 10. If you have only that, you don't have any other waves, you're going to be measuring only that. So this is the wave action density. For now, just think about this. How much energy is there in each wave number? And if you have only the short wave and no longer waves, you'll be measuring this. But then if you introduce long waves with the steepness of 0.1, which is the ratio of height to wavelength, approximately, then now that you have this long wave propagating through, what it does is it smears the energy of the short wave in adjacent wave numbers, so you will have energy in a variety of both lower and higher wave numbers, and actually most of it is going to be at the ends of the distribution. So the original wave number is actually going to be the least observed, and the more you increase the steepness of the long wave, the more you spread it out. So now suppose that you're measuring the short waves and you have longer waves, you'll be measuring this. And that's an important thing to consider when interpreting measurements, when you have short waves in present or without long waves. So one possible way to look at this is through linear wave theory, which provides a set of elegant solutions that describe the distributions of velocities, pressures, forces under a long wave. And even though it's a linear wave theory, it allows for computing higher order nonlinear quantities. And regarding modulation, the early analytical solution was by Longuet-Higgins Stewart in 1960. And basically, they, through theory, they derived peak modulation at long wave crests is proportional to 1 plus epsilon L. And this epsilon L is the steepness of the long wave. So if you get steeper long waves, this modulation will be higher, and it's linear with that. And it peaks at the crest, it's lowest at the trough. We'll see what it looks like graphically in a bit. And this has been basically the result that's been, referenced and reused a lot, with not much revisiting until the numerical simulations by Perret and colleagues. And what they found is when they solved the full equation set to see, hey, did Longuet-Higgins Stewart miss something by dropping the nonlinear terms to be able to get the analytical solution? Then they found that actually short waves grow indefinitely due to convergence by long waves, the longer you integrate the solutions, which is
Grow in magnitude, grow in length.
in magnitude.
Grow
Yeah,
in
and I'll show. And they're also sensitive to initial conditions. Basically, depending on how they initialize the field of short waves in the simulations, they found that, it can be unstable or it can be stable. We'll see that in a little bit. So these top science questions are, do stable solutions exist for more realistic long wave trains and groups? Are they different from the classical result and from recent simulations, and why? And should they be incorporated in spectral wave models beyond the current state of the art? Or can we at least inform better this term? Okay, so we'll review the governing equations. This is the dispersion relationship for deep water waves, so this will apply to our short waves. Omega is frequency, K is wave number, G is gravity, and U is ambient current. So this basically just relates your frequency to wave number, and the frequency can change for the same wave number if you have higher or lower ambient current. And in our case, our ambient current is going to be a varying current due to long waves. Now, this relationship does require that U doesn't vary significantly on the time scales of the short waves. So there's a scale separation here. If we pick a short wave that's just short enough relative to the very long waves, what that short wave is going to experience over its one phase, U should more or less stay the same, or not very much. And we'll also use this conservation of wave crest. This also comes out of linear wave theory and conservation of wave action. In the conservation of wave crest, basically what this tells you is that the wave number will change over time if you have a gradient in frequency. And for the conservation of wave action, basically it's a simple, conservation equation. For wave action, wave action is simply just energy divided, scaled by frequency. So we use action rather than energy because energy is not conserved when you have currents or varying currents, but action is. So this is the equation to use. And this is the equation that spectral wave models for prediction are solving, except that there are those source and sink terms on the right-hand side. So here there's 0, which means that we assume there's no wind and there's no wave breaking. So we're looking at very gentle, gentle long waves that are perturbing the short waves that are not close to breaking. And for the long waves, we're just reusing the linear wave theory solutions. So elevation eta is going to be simply a cosine scaled by the amplitude. U and W are orbital, horizontal, and vertical velocities from the long wave. So they're also, cosine and sine, but they have this scaling in the vertical. Basically, in the solutions here, you have k times z, but we're simply following the elevation of the surface waves to evaluate U and W at the surface, and that's why we have this this exponent term. So this part is important to get to the nonlinearities. And for now, we're assuming no vertical shear, but there is a theory by Stewart and Joy that allows us, under certain conditions and assumptions, to basically calculate the appropriate effective depth for the waves rather than evaluating things at the surface. But for now, we're not doing that. We're just assuming no vertical shear. And then these are just expanded equations for the short wave. So these are going to be our equations that we'll be solving. So you have change in wave number over time depends on basically advection by short wave group speed. So that's just propagation of waves. If you're watching it waves, on the water surface, they're moving. So that's this term. U times this is a Doppler shift by ambient current. And this is the convergence divergence term. Basically, wave number will increase if you have this negative and vice versa. And then there's this weird term that has the gradient of gravity in space, and this only occurs because we're allowing for gravity of the short waves to vary. It'll turn out that this term is important to have. If you allow this to vary, you have to have this term to stay conservative regarding the short waves. And the equation for wave action is actually very similar to the wave number one, except this last term here is the gradient in the short wave group speed. So that term we'll see that it's important regarding having stable versus unstable solutions. Okay, so first I'll go over analytical solutions. And we can't just get analytical solutions for any equation. We need to drop a lot of nonlinear terms to get to something manageable. And here we're just assuming that, okay, by dropping this term, we're saying short waves are not moving. They're just kind of, a tracer field that is, staying there. And we're dropping these variations of gravity in space. So you get this, and then this you can integrate to get a solution. And so the solution from Longuet-Higgins and Stewart was basically, recall, I said it's scaled with 1 plus epsilon, and now this is a phase-dependent solution. So it scales with a cosine of the long wave, which means that it's going to be highest at the crest, lowest at the trough, and have exactly the shape of a cosine, which means that it's going to average to 0, which we expect. However, this solution you can obtain only if you evaluate all the quantities at z equals 0, so if you don't follow the long wave surface. Now, if you evaluated z equals eta of the long wave, then you get something a little bit more nonlinear. There's this nested exponential thing. And this actually, if you Taylor expand it and keep only the first order term, then you get this. So it's consistent with the Longuet-Higgins solution if you linearize it, but it's actually nonlinear. Now, one question that comes up is, well, is it appropriate to evaluate things at quantities at eta rather than z equals 0 in the linear wave theory, because linear wave theory assumes small perturbations? And my argument is that yes, we should, because there is an existing argument in favor of that, which is Stokes drift. Stokes drift is this phase average Lagrangian quantity that basically says if you have a long wave field and you have some tracers, overall it's going to drift due to the motions, and it can only drift forward if you evaluate it at eta. and there is just abundant evidence for Stokes drift observational. We know that it happens. So if we can do it for Stokes drift, we can do it for this as well to get the higher order nonlinear solution for the wave number.
Why not? Why not at eta over 2? In other words, the mean depth of the fluid. Why go all the way to the base of the troughs? Is that what Z equals eta is? Z is equal eta.
Eta means you're following the surface.
Yeah.
Yeah.
Okay. It's at the height of the mean, not the height of the trough. Eta. Z equals eta.
Z equals eta mean like if
It's the
if
height
this
of
black
the-
line if this black line is the elevation of my long wave,
Yeah.
it means I'm gonna evaluate quantities at that surface rather than at the mean level.
Eta is a function of that.
Because short waves are riding on the surface,
I see.
so we want to evaluate their properties at the surface.
I see. You're evaluating
So that's
on
what-
a
That's what Longuet-Higgins Stewart
surface.
did not do.
Okay.
They followed Z
Alright.
equals 0.
thing.
Okay, so recall that their solution is just a cosine. And what's on the y-axis is the modulated wave number normalized with its resting wave number, so that we have a nice resting thing at 1. And so the black line is just a cosine, but the nonlinear solution actually amplifies the crests, and it also amplifies or reduces the troughs. So overall, on average, you get higher values, and this is like this relative to this is like a 20% thing. Now, if you calculate that and take the max and mean values of the modulation as function of steepness, you get the Longuet-Higgins being just a straight line, simply because it's 1 plus epsilon. But the nonlinear solution increases up and actually diverges. The steeper you are, you diverge further from this line. Now, it's debatable how far in steepness we can go for these solutions to still be valid, because recall that linear wave theory does assume small steepnesses. And I go up to 0.4 simply because 0.4 is there about the steepness at which most waves break. You don't see many more steepnesses higher than that. I just came from an in-depth overview of wave breaking from theory and from observational lists last week at a conference, and they showed a scatter of steepnesses of observed breaking waves, and it's like a cloud all over, but they're mostly in this range. So actually I'm satisfied to just stay up to, let's say, 0.2 when most waves are not breaking, just to sort of stay in the safe range of the theory. Now notice the dashed lines are means, and recall because the Longuet-Higgins Stewart is a cosine, the mean of that is always 1. But the mean of the nonlinear solution is higher than that. But I will show that that's actually wrong. It shouldn't be, because our wave numbers need to stay conserved. If we get a mean that's increasing, that means they're not being conserved. And I'll show you that this non-conserving property comes from dropping the terms that are responsible for conservation. And just a little bit more about the shortwave gravity. If you evaluate it following the long wave surface, you get from the first order linear theory, you can get this exact solution, which if you unroll it, you can go up to fourth order. But basically, notice that the scaling factor for G is 1 minus something that's basically always positive. So it's always a decrease in gravity. overall. And this is what it looks like if you just consider, actually I don't have it labeled here, but if you don't have long waves, your effective G over G resting is 1. But now if you consider the first order solution for the gravity perturbation, you get is blue sign. But as you go higher in order, that basically disturbs the shape of the curve. So the second order deepens it at the crest, at the troughs and crests. Then going to third order actually shifts the whole thing down. And for fun, you can also evaluate it in a Lagrangian frame where you follow the short wave and basically tracking what its gravity as it follows the surface, and that gives you a further decrease. But basically, the biggest jump is from nothing to blue. So you have to have that for interesting things to start happening. But to second order gives you a further amplification, and then from there the changes are minimal based on my simulations.
And that's because the restoring force on the shortwave is different on a curved surface than it is on a flat surface?
No, this is not why, and actually I'm not considering the slope of the surface. This is purely because at the crest we are accelerating down.
Of the shortwave?
Yeah, so if you swam or surfed in a long swell, you feel lighter on the crest and you feel heavier in the trough.
I see.
Because trough is pulling you up. So the reference frame is distorted. So that's happening to the short waves. So short waves feel lighter on the crest and they feel heavier in the trough.
I see. It's an acceleration, not a curvature.
Yes, but it's possible to consider the curvatures as well, but I think the math gets complicated. And this is the same thing, but looking at basically max values, or in this case, min values, as function of steepness. And this is what I was saying that, so if you, oh no, I'm sorry. These are phase averages. I think to me this is even more interesting. So if you're looking at only first order, your average gravity stays the same because you're just a cosine. But if you look at higher order terms, then you have pretty significant. This is for a very high steepness, at second order, you reduce by 7%, and in third order by over 15%. But let's say even in more gentler things, more gentler steepnesses, you're on average few percent lighter, and it's kind of a weird thing that on average your gravity would be decreasing just because there are waves.
You spend more time in one place than the other.
Exactly, spending more time at the crest than the trough, because you're going with the crest.
So there's
Sanjay.
Okay, so just to understand this thing, like the short waves are present because of the background wind, right?
There's no wind. Background long waves.
No, but then just the presence of like short waves. Like I'm curious to see like whether this behavior for like the gravity or for the wave number, does that change for like different wind speed, or is it like is that something that is not being considered?
It's a separate process which I'm not considering. So we're looking at no wind.
But then the short waves are being generated by the wind, right?
Yes.
Okay.
Yeah.
Indeed.
So the hypothetical scenario is the wind blew for some time, generated ripples, and then wind shut off, and now you send in some long waves through. It's not a realistic scenario, but it allows us to isolate the specific process of hydrodynamic modulation.
But in the wave tank, can you jiggle your wave maker such that it makes a combination of long and short waves?
I'm thinking about how to do it.
Yeah.
Okay, so now some numerical solutions, and in which case I'm not considering all the terms. Recall that for analytical solutions I had to drop the nonlinear terms. Now we're considering everything, and first the simulations by Perret, which in part motivated. This is the figure 2 from their paper, and don't worry too much about the labels and what the curves are. But all of this is saying to you is that if they initialized with the Longuet-Higgins analytical solutions, they get a stable solution of things just like they're mildly growing. But then if they initialize from homogeneous field, things just explode. And that's kind of weird, but they had there is a physical explanation of nonlinear terms simply amplifying things. I'll get to the animations to show you that. Yeah, basically these nonlinear terms are effectively responsible for having the instability, and the conclusion was, well, the original Longuet-Higgins Stewart solution, it's not really applicable in general because waves will just amplify short waves until they break. I mean, this is effectively 10 times the modulation. Things are already like breaking it down here. Okay, I will accelerate a little bit now that we went through the equations. So the model setup is essentially following Perret et al., and the equations to solve are the ones I showed earlier. Numerical schemes. This is my scale separation, so I have a long wave number of 1, short wave number of 10. Separation of a factor of 10 is a pretty good one from the point of view of the orbital velocities being more or less stationary currents. Initial conditions, okay, so they're very important, and Perret found stable solution if initialized from LHS, I already said that, and unstable growth if initialized uniformly. And in their description, so I quoted their scenario of sudden appearance of a long wave perturbation in the middle of homogeneous shortwave field. Basically, they're describing the physical scenario in which there's unstable growth, but then they say, okay, this is, you can't really imagine a real scenario in the ocean, but this is what the equations say. And then as I was doing my own simulations, I found a weird thing. So I'm going to show you how this evolves over time. Let's see, where's my mouse? Okay. So black will be the elevation of the short wave, so that's the water surface. And then orange will be the modulation of the wave action, or just think energy. So the wave height, the short wave height is increasing. And the blue is the wave number. And this purple will be the nonlinear term that turns out is a culprit for the instability. And I want you to just notice that the orange and blue patterns are not in phase with the elevation of the short waves. They're actually moving slower. And as they're moving slower, the long waves are just propagating through this pattern and amplifying it with each time they propagate. And this nonlinear term, now look at the purple curve. We're now 5 periods in, it has growing. Basically, the modulation perturbations of the short waves being kicked out of the phase pattern of the long wave makes them unstably to grow. And this term is responsible for pushing that growth. So it's no longer the actual convergence and divergence.
So what is the time scale here? T is what?
T is long wave periods. So I go from 0 to 10, basically 10 periods.
Long wave period. Okay.
So you see that in only 10 periods of the long wave, these things just explode.
So the short waves have ridden like 10 waves
Yeah.
by the end of it. Okay.
Yeah. And you don't really see in a nature that short waves amplify like that over so few long wave periods. This is what this looks like in a view that's on the y-axis. We have time, long wave periods. This is the initial phase of the long wave. So the long wave crest is moving from left to right diagonally like this, and basically bunching and dilating the short wave, but the short wave signal, the modulation perturbation is moving. Basically the slope of this line is the group velocity of the short wave plus Stokes drift. And if you follow this signal, it just amplifies and blows up. This is wave action, wave number, which remains stable, and the steepness. Steepness is the key for reaching the breaking condition of the short waves. Now in numerical simulation work, it's very common to introduce ramps to make things start smoothly and not introduce shocks. So I thought back to that scenario that said, okay, you have just a field of short waves and all of a sudden there are long waves. That's pretty unrealistic. So I just tried ramping up the long waves, and it turns out if I ramp up the long waves and then keep them on at max amplitude thereon, the solution is stable. So actually something weird happens at the very beginning if you don't ramp up the solution. Now, the ramp is not very physically satisfactory, so I thought, what if I emulate a wave group? And real ocean waves come in groups. And nice thing about groups is that they kind of have a natural ramp. So basically, in this simulation, I just force my long wave to follow this group pattern, amplifying and then decaying. And this is not a real group, because it's not dispersive. I'm really just changing the amplitude of the wave with time. So you can think of this pattern as just a group of waves moving through, but they're not really dispersive as real groups are that you see on the ocean surface. But this is, for the sake of the experiment, this will do. So now if you do a group thing, you get amplification of modulation and then decaying. This is for the steepness, so you see you get max steepness modulation here at about period 5, which is when my peak of the group is. And this is about 0.2 for basically 20% modulation at the yellow for a steepness of 0.1.
That's the steepness of the short wave?
Of the long wave. So we're looking at everything in the context of the steepness of the long wave, but we're looking at how do the short waves change.
N and K are properties of the short wave. You're saying AK is the property of the long wave itself?
Okay, so we have modulation in wave energy, so in height. We have a modulation in the wave number.
Of the short wave.
And then those two combined, yes, the short wave, and those two combined, we look at steepness of the short wave.
That is the steepness of the
Yes.
short wave. All right, I got you.
And now just to show you what happens in this scenario, I'm getting close to the end. When we ramp up the long waves, it turns out that the short wave modulation signal never gets kicked out of the phase of the long wave. Basically it stays, it follows it, it's locked in. So this term never gets to become large enough to basically grow the modulations fast. And at least to me, it's kind of we gotta be careful to not look for results, with a bias selectively. But when I look at ocean waves out there, it's actually much more common to see, the rippling to be enhanced following the crest of the long wave if you pay attention. And this is just a bit different view to dissect these tendency terms. So here, rather than giving you math terms, I'm just calling them by their physical interpretation. The propagation term, advection, convergence, and inhomogeneity, and I average that of the long wave phase of the long wave phase to see which term contributes most to this unstable growth. And green is the convergence term, so that's our initial driver of the growth of modulation. But as that grows, the nonlinear inhomogeneity term grows with long wave periods, but on average it's always positive. So it goes through its little negative dips, but overall it's more positive, and that amplifies this instability. And for contrast, if you have a ramp, the inhomogeneity term ends up oscillating symmetrically around 0. So you never really get an unstable growth there. And this is what it looks for groups, and this is very interesting because it's a completely different picture from the previous one. What you see here is that when you're on the front face of the group, when the long waves are increasing, you have positive contributions to the short wave tendencies. But then when the long waves start decaying, now you're on the tail end of the group, these basically reverse sign. And this was confusing me for a while because I expected, okay, as the group propagates through, short waves get modulated, but then they should stay like that. But that's not true, because recall that the convergence is actually a forcing. So when you start reducing the amplitude of the long waves, that forcing reduces, and that forcing is required to maintain the modulation. So if you remove the forcing, the modulation goes away. And I think this is my final summary plot, basically looking at analytical solutions and the numerical solution, in which I pull out just the maximum modulation. And what this shows you is that up to about 0.25, numerical solutions are almost exactly the same as analytical in terms of modulation, which tells you that the nonlinear terms don't really add much, but they begin to add much to the solution for higher steepnesses, for which, it's debatable whether we can rely on this equation set. But at least for this, like up to say 0.2 or 0.25, they're almost exactly the same, which means that we can actually use the analytical solution for these gentler steepnesses without solving the numerical simulations. Okay, I'm gonna skip this in the interest of time and just give you my takeaways. Higher order solution for short wave wavenumber yields stronger modulation at crests relative to the original solution, the Longuet-Higgins Stewart, about 18% larger for 0.1 steepness, and about 38% larger at 0.2 steepness. And the numerical solutions are consistent with previous work by Perot in an infinite wave train, so we can reproduce this unstable growth, but also explain it. We know which term is responsible. But we also found that actually this is more an exception, like it's an edge case, rather than a typical setup that we expect to see. So if we have something like long wave groups, which was more common in the real ocean, then the solutions are stable. And the numerical solutions are consistent with exact analytical solutions up to this steepness. And I have a list of to-do sort of what are the next steps with this, like what we can do. We can easily consider misalignment of short and long waves. That basically factors in a cosine term in there. We need to quantify the scale separation to know exactly for which combinations of waves is this valid. Can we observe this in the lab? That's more of a future work thing. And then considering how can this inform the current source terms the dissipation terms in the spectral wave models. And I'll end here. Thank you.
Then anyone have any? Do the mic?
No, you should just go there and ask some questions.
Alright. Anyone have any questions for Milan?
How would you think the Stokes wave, if long waves were Stokes wave, affect these solutions?
I thought about it a little bit, but I think it can be worked out. It's really about replacing eta equals a cosine with the 3 or 4 terms that you have there in the Stokes wave. And yeah, I believe we have orbital velocities also readily available for the Stokes wave as well. So I think at the very least numerical solutions should be feasible. I'm not sure if we can do analytical.
Would you think that would bump up the nonlinear term?
Yeah, I think so. Yeah, basically, Stokes wave is a higher order wave that is more, it has more peaked crests and more elongated troughs, but it has an analytical form for elevations and velocities. So I don't think an analytical solution integral would be feasible because of, what made my analytical solution feasible is that eta is just a cosine, and that made it nice for integration. But with the Stokes wave, I'm not sure, but numerical solutions definitely.
So these are based on deep water wave, linear wave theory, which is monochromatic, single peak frequency, uniform wind forcing, and then you take it away.
Yes. However, it's possible to then linearly superpose multiple long waves or a spectrum of long waves. Say, let's look at what a John swap spectrum does to a very short wave, and it's gonna be a milder effect, I believe, because here we have, with a single monochromatic wave, it's like, we're really we're emphasizing the process.
That's where all begin with.
Yeah. Ron.
Yeah, interesting stuff. I've worked on this from the radar perspective when I did my PhD a long time ago, and our main paper at the time about this modulation was Alpers and Hasselmann 1978, where they derived the linear modulation transfer function, the hydrodynamic modulation transfer function. And the beginning of your presentation was very much like what they are doing there. And so then of course you go further, and I had the same kind of question that Payson had with the Stokes wave. It looks as if you are already accounting for some variations there. And with the Stokes wave, it would somehow be more complete than accounting for some variations, but still assuming it's sinusoidal, right? But my main question was a different one. It looks as if, like you mentioned the scale separation, that it looks as if at the moment you are considering only one short wave riding on one long wave with certain wavelengths. Now, if you make your short waves shorter, they will become slower, right? And have maybe have more time to interact with the long waves. But if you make them longer, they will have a longer relaxation rate, maybe experience a larger modulation because of that. So I can imagine if you change the wavelength of the short waves, you will probably find some kind of peak somewhere at some wavelength where the stuff that explodes like that, what you showed there, or that the modulation becomes very strong, that it has maximum, right? It will not be like the same for all short waves, but for some short waves it will be particularly strong. When you make it longer and shorter, it will be less. Have you looked into that a little bit already?
Not yet, but I will. I think there's a lot to go in depth and in detail here, and at some point I also need to make a choice. What makes a paper and what makes an X paper?
Yeah, I think it could be good to look into that a little bit, because it could be your results there could be really different when you have slower or faster waves.
Yeah,
and it would be
yeah.
good to get a little more overview of by how much the results will be affected by that.
Yeah, I think at the very least these two are feasible, and to add Stokes wave with a numerical simulation is also feasible, I believe. Yeah, but the thing that you're asking, I could probably find an analytical form for that. Basically, finding a maximum for the K short over KL, or the other way around. That
It would
maximizes
be
that.
interesting to know not only where the maximum is, but also how pronounced would the peak be, right? Is it just a little maximum, or is it really a strong resonance somewhere that gives you really a strong effect? When you go away from it, it becomes much weaker, or or is it not such a strong peak?
Great, yeah, that's very helpful. Thanks.
Any other questions from the public?
Essentially following up, is it different for short waves going with versus against the long wave direction?
Yes. Yeah, okay, so do not go back. It's all about, so long waves with their phase speed, the field of short waves moves with their group speed. So it's really about the relative difference between those velocities that will determine how slowly is the short wave moving through the convergence field and how slowly is it moving through the divergence field. And we have an analytical solution for if they're not moving. That's easy. But then we can only do it numerically if they are moving. And so the shorter the short waves, the smaller then their group speed will be, assuming we don't go into capillary waves. So they will be approaching this analytical solution value. Now, the longer they are, they will be spending more time doing nonlinear stuff.
Especially if they're going in the same direction, get it wrong.
Yeah, and the nonlinear stuff is what amplified the modulation.
This might not be a question, but like a comment. So for your third bullet spot, bullet point, if you remember Shabani's paper from 2021, where they basically did the same thing as you assume in a model. You have a homogeneous shortwave field, and then you send out a signal of long wave into that field, and they conduct that in the wave tangle Australia. What they really observe is that the short wave were actually really enhanced on the leeward side, while the longward side were stretched, and you can't see any energy of the short wave from the phase average result. So I think this is definitely observable, and you can do that in sustain for that part, yes. But for the nonlinear and homogeneity part and the wave actions, we don't maybe.
Maybe, yeah.
So,
Shen.
like a simple practical question. So, if what you presented is applicable to the real ocean, like what scale are we talking about of interaction? Like the long wave and the short wave, what are they in the ocean?
Typical for the long waves, typical swell scales. So waves that are long few hundred meters, let's say, and for the short waves, basically any wind waves. So yeah, up to let's say a few meters.
Anyone from online questions? All right, everyone, that concludes our 51st Compass of the season.
Thank you.
From Dr. Milan. And then you'll be emailing the slides?
Yeah, I can email the slides.
Okay, so check out the email recording from Roland, and that will be the slide conclusion. So